So our next speaker is Zeljko Ivezic, who's a professor of astronomy at the University of Washington and project scientist for the Large Synoptic Survey Telescope, affectionately and understandably known as LSST. Dr. Ivezic is involved with optimizing LSST for asteroid discovery. So please welcome Dr. Ivezic.
Hello. I'm an astronomer at the University of Washington, but I spend most of my time working for a project called LSST, which stands for the Large Synoptic Survey Telescope. And that will be a new telescope system that is an amazing discovery machine for new asteroids. And so as we learned from previous talks, the first step in protecting the planet from asteroids is to find them. You have to detect them, you have to establish that they are dangerous ones, and then you go on from there. So I will first spend a few words explaining why is it hard to find these small objects, and why do we need a special kind of telescope. And then I'll tell you a little bit more about this new special kind of telescope, LSST, and how exactly we will find these new objects. So the point of this diagram is to show asteroids in main belt relative to Earth and planets. Inner planets are in that black circle in the middle. The inner radius of that colorful range of dots is Mars orbit. And the point is that despite the word near in the name near Earth objects, these objects spend most of their time far away from Earth. As you can see, it's not easy to see in this light, but they spend most of time either in the main belt where these lots of dots are found, and then they occasionally come close to Earth, or they live inside Earth's orbit and then they occasionally come close to Earth. And that is more quantitatively shown here in this diagram. So this vertical axis, this is finicky remote control. So the vertical axis here is the distance from Sun. Basically, it's from Sun this way out. And this line shows where you typically find these objects. And as you would expect, there is a peak at one distance Sun-Earth, because they are near-Earth objects. That's how you find them. But there is this long tail of objects all the way out to orbit of Mars and beyond it. So the main point to take from this diagram is that lots of objects spend lots of time very far away from Earth, and that's why it's hard to find them. To see them on the sky as very, very faint objects, you need to have a large telescope. That's conclusion number one. Conclusion number two, when you ask where on the sky you find them, basically the answer is all around the sky. It is true that they dominate this plane across the sky called the ecliptic, but now if you look carefully, this is visualization of real asteroids that we know about. You can see many dots that go all around the sky. So conclusion number two is you have to monitor the whole sky more or less. And it turns out this is not so easy to do at the same time, both to see very faint objects and to cover the whole sky. So if you were going to cover the whole sky, this is roughly how you would do it. This yellow dot is so-called field of view. This shows the picture on the sky of what would you see through your telescope. And this particular yellow dot is very large, much larger than what typical telescope can see. Typical big telescope can see much less at any given moment than full moon on the sky. And this yellow dot is 7 times full moon across the sky. It's a humongous field of view, and yet it takes many, many of them to cover the sky. And if you want to do it every few nights, that means you don't have much time per single observation. And that tells you you need to have a large telescope in order to see faint objects. So in addition to large telescope and large field of view, you also need humongous camera, because once you have this large field of view, you have to put detectors to get this image with many pixels. It works out that that yellow circle from the previous diagram would require about 3,000 megapixels to cover. The camera that you have at home, probably when you playing tourist and going around and making pictures is few, maybe 10 or 20 megapixels. We need about 3,000 megapixels to cover that yellow circle. That's expensive. That's over $100 million to build. And then, if you're making these zillions of pictures every minute you get 3,000 megapixels. That's humongous amount of data. Works out to be about 30 terabytes per night. 100 terabytes in 10 years. You need very sophisticated software to handle this data flow and to process it. You cannot have people looking with their eyes at this data. So it's a very sophisticated system, and you cannot avoid it, because these objects are small, they are far away, and they are all around the sky. So you must have a very special system. And the bad news is we don't have such a system. The good news is we are building such a system. And that is LSST that I told you about. That's one of the main 4 goals of LSST, is to enable such observations. So here is artistic concept of this observatory. It will be sited in Chile. It will start in 2020. Its main goal is to obtain about 1,000 images of the night sky visible from Chile in about 10 years. You can think of it as a movie of the sky, because we have 1,000 pictures, not just one. We have essentially frames of a great movie. Indeed, we call it the greatest movie ever to be made, because it will take you a full year of interrupted viewing to see every piece of data, of imaging data that LSST will obtain. It will be a remarkable technological achievement. And once we look at those images with software and find objects, we'll detect 20 billion galaxies and about 20 billion stars. For the first time in history, astronomers will have cataloged more objects than there are living people on Earth. It never happened before. We could name one galaxy or more, and one star after each and every one of you here, and all around the world. All of you who are watching this on the web, you can get your own galaxy and your own star. And there will be about 5 million asteroids. Only special people will get their asteroids. There are only 5 million of them. And the reason why we want to look after asteroids is twofold. One is just to do science of the solar system, and the other one is, context of today's asteroid day, we want to look for dangerous asteroids. So let me just quickly show you some of the characteristics of this new telescope, and then I'll show you how we will find asteroids. That's me trying to speed up the construction, because I'm very concerned about asteroids. I'm here. I have to disclose, I didn't do much because the door was closed. It was locked. Our project manager does not allow scientists to operate heavy machinery, because we could hurt ourselves. So that's done by other people. This is example why LSST will be so much better when you look at the quality of images. This is image from SDSS. This is like gold standard today. One of the best that we could do today if we want to cover the whole sky. This across is about 1/10 of moon's diameter. You can see one galaxy here and another star in here. And this around is pretty much black. It wasn't sensitive enough. It was tiny telescope, 2 meters across, not sensitive enough to see many faint objects in this part of the sky. This image is obtained with much larger telescope, very similar to LSST, about 8 meters across. And you can now see this is the same part of the sky. This galaxy is the same as there, and this star is the same as over there. This is what happens when you have a much bigger mirror. You collect more light, and you can see many more faint objects. So we can already make images like LSST will make. However, we cannot make it across the whole sky. Again, this is 1/10 of the moon's diameter. And now we'd like to go from the whole sky with such images to this quality, but again over the whole sky, not just teeny tiny fraction of the sky. And for that, we need this new system. And so the trade secret of LSST is its large field of view. It is true that we have remarkably large mirror. This mirror by itself costs $30 million, just the mirror. But there are other telescopes with similar mirror. There are about 10 telescopes in the world that have similar mirror. So we are big, but we are nothing unheard of. However, combination of large mirror and huge field of view, that is unheard of. This is the trade secret of LSST. This is why we can, for the first time, detect tens of billions of objects. At the same time, we can see many objects per unit area on the sky, and then we have this giant circle that covers big part of the sky. And that's why we can cover sky in about 3 nights, the whole visible sky, and then do it over and over and over, make this great movie of the sky that will tell us what's changing on the sky, both in brightness and what's moving on the sky and perhaps heading to hit us in the head. That is the trade secret. Again, when you have such a large field of view, you need to have a remarkable camera. We'll have the largest camera ever built for astronomy. It's being built about 50 miles from here at SLAC National Lab next to Stanford University. So the focal plane, these 3,000 megapixels will be found in here, and the whole camera is the size of a small SUV. You can see a person over there. It's much bigger than when we say the word camera, what we think of as camera. And so now, once we will build this system, we will start with operations in about 2021. This is roughly, indeed, what we plan to do with LSST. We plan to scan the sky about twice per night. Then we'll come to the same point on the sky a few nights later. The remainder of my talk in a few slides, I want to now explain these 2 technical aspects. Why do we want to do it twice per night? And then why do we have to come back a few nights later? So the reason why we need to do it twice per night is that when you go to this faint level probed by LSST, then there are so many asteroids on the sky that these dots are asteroids on the sky. This is roughly, I forget, maybe a few full moon across. And so each of these little dots is one asteroid. And when you look at their mean distance, typical distance between these 2 dots, it's much smaller than the size of this line. And this line shows how much they move on average in 24 hours. So now imagine we make a picture like this tonight, and then we make another one in 24 hours, but all these dots got scrambled because they moved much more than typical distance. How do you know which one is which? They don't have any details. They just look like point sources. Pardon me? We'll use mathematics. But we'll help mathematics. We could solve it by mathematics, but it would take a lot of computational time. That's an excellent idea. We're working on it. But until we figure out if we can do it, we are planning strategy in which we'll get two observations per night within an hour. So these points, they will not move this much. They will move maybe 5% of that. It will move like my finger. And then you will have pairs of points that are very close to each other, and you know that these 2 pairs are together. These 2 points in a pair are together, and they'll tell you which way that asteroid is moving. And then, once you have these little vectors, then they will tell you how to connect the dots. This is the most sensitive remote control I ever used. There we go. So that's the idea. That's why we do 2 observations per night. Once you know which way it's moving, then you still have to do math, but the math becomes much simpler, and we can do it much faster. That's why we do it twice per night. And in practice, you don't, of course, use your eyes. You use sophisticated software. So this is example of how computer knows that we found moving object. This is image of sky, same part of the sky a little bit later. And image basically means a bunch of numbers. Each of these pixels now is one number. It's like 64,000 shades of gray. You have these numbers, and then you color code your pixel. That's why you think you see image. These are just numbers. And then you take this bunch of numbers, and you subtract the other bunch of numbers pixel by pixel, and then you get the difference. So it's very similar to blink comparator that Clyde Tombaugh used to discover Pluto, except computer is now doing it, and it's more powerful than million Clyde Tombaughs. It can do it much faster. And so difference of this image shows black spot, white spot. That's because there was asteroid in here. So we subtracted 2 minus 1. You have light here, but there is no light there. That's why this is bright. But this guy was here before, and there is nothing in here. So nothing minus this gives you black spot. That's how computer can learn that something was moving. And then computer says, I found spots in difference image. And then basically in the next step, you connect the dots. So we have 2 observations per night. We have pairs of dots. And then computer says, well, let me connect these dots together. Now let me try to connect more. At the end, it tries to fit orbit. And because we know in what gravitational field these objects are moving, there is Sun, which is dominating, there is Jupiter, and then there are other planets. We can calculate these orbits precisely. We can ask, are these dots consistent with a given object moving on the sky? And that allows you then to weed out all the junk connections of these wrong connections of dots from the real ones. And with computer, you can weed it very fast, and you can be very precise in your estimates of which objects are real, which are not. And so the prediction is, can we go one page back? The prediction is that after 10 years of using LSST, doing science with it, but also looking for moving objects, we'll end up with about 5 million asteroids. Today, we know less than 1 million. And these asteroids will have orbits. They will have beautiful color measurements. We'll learn a lot about them. And then, in addition, we'll have 40,000 so-called trans-Neptunian objects, which are found in the outer part of the solar system. And they are very useful for doing science, for studying, for testing theories for formation and evolution of solar system. And in the context of Asteroid Day, we predict that we'll detect about 100,000 near-Earth objects by using the same tools that we developed for doing science. So that will essentially come out with the same survey. There will be no extra survey. We just get 100,000 near-Earth objects, and we will basically get to the sensitivity level that was given in congressional mandate to NASA to accomplish, to minimize risk to people, to find 90% of objects that are 140 meters or larger. Basically, that cutoff corresponds to cutoff for causing large tsunamis and a lot of that. And if you remember now, talk by Clark Chapman 2 talks ago, he went through the whole thought process of this mandate. But LSST is the only ground-based survey that is being not just constructed, but even planned, that is capable of, can we move one page forward, that is capable of fulfilling this mandate. So I'll stop here and take questions. Yes? The question is whether LSST will not be out in space. No, we would love to put it out in space, but it would be enormous cost. So all the telescopes that would go out in space that are planned to go or that went, they're much smaller than LSST. The reason that LSST is on the ground gives us opportunity to make it so big. Now, there are other ways of finding asteroids, and Rusty Schweikert mentioned those space-based spacecrafts that would go either close to Earth and then look along Earth's orbit, or they go close to Venus and then look towards Earth and find what's moving. So these are complementary approaches, and scientists, engineers, and government and NASA are working together to find out what would be the most efficient way to find them, most efficient in the numbers, and also cost-benefit analysis, how much would it cost, and so on. This is ongoing process. I anticipate that in a couple of years, we will know better what government wants to do. Dave? If LSST finds an asteroid that will hit Earth, I didn't hear the rest of the question. Not LSST, no. The purpose of LSST is to find them and measure their orbits as well as we can. But we are not in the business of estimating precisely whether it's an impactor, and we are not in business of doing any deferment. That's these other missions and other organizations that are planning to do that. Yes? Models for what?
For detecting.
The question is, if LSST predictions are based on empirical models or not. So it's a combination of two methods. One is to take simulated asteroids, simulated orbital parameters, make simulated populations, which means computer imagines hundreds of thousands of asteroids, and then tells you if at a given moment you look in that direction, that asteroid will be that bright, and then you look at how you simulate observations of LSST, and you ask, would I observe, would I detect this object if I point it this way? And then you do complicated mathematics of calculating orbits and everything else. At the end of the day, you ask what fraction of objects that I put in I recovered. Now, there are various assumptions that go into your simulations. And so each significant part of these simulations, like for example, is it enough to have 2 observations per night and then many pairs that come online every 4 or 5 days? Is that enough or not? This is now separate simulation with software that was tested, that was verified to a large extent in some other surveys. Then how well can you predict sensitivity of telescope? That depends on atmosphere, on observing conditions, and so on. That is also to a large extent verified by other instruments. So all the components are verified like Lego blocks. You can say each Lego block is that strong, and then you make a house and you say, when I sit on it, will it break? Well, if you do calculation, you can say it probably will not, but until you sit on that house made of Lego blocks, you don't know. Now, we are hopeful based on other simulations we did in other contexts, it's likely that it will be fine. But if you have any lawyery background, if you're a lawyer, then yes, we cannot prove it until we do it. I didn't mean it in a bad way.
Thank you very much.
Thank you.